Hello everyone, welcome to our senior project final presentation. Our group created a fire detection system, and the members of the group include Sal, Jarek, Chris, and myself, Noah. The main drive of this project started back in the early months of the fall 2020 semester with the emergence of the devastating wildfires throughout the world, especially in California and Australia. In response to the millions of acres burned in 2020, our group decided to be proactive and create a fire detection system. The main issue is the lack of early fire detection for the homeowners living in remote areas or have large open land. The goal was to create a consumer accessible product that can be implemented on these homeowners' properties. The main components of this project include a camera on a rotating servo that transmits video to the object detection software, along with the sensors that detect low soil moisture, and a buzzer to alert the homeowner. This was completed by taking advantage of many open source programs such as Label Image, Darknet, and of course the Python and Raspberry Pi and the Arduino to achieve these results. Now getting into the market research. The main objective of this project are increasing safety and ensuring the conservation of the environment. However, that does not mean we are immune to the environmental, ethical, political, and social constraints due to the technology being included in this project. Some potential ethical and political constraints that can cause an issue include the use of a camera with object detection due to the ongoing debate about privacy. However, the intended location of the system would be on private property with the owner's permission. False alarms can be a potential social issue as well, so we want to ensure the detection accuracy reaches a certain threshold before alerting the user of a fire. Now, Chris will go over the project plan.
Hello, I'm Chris Kripke, an electrical engineering student working on this project. I oversaw image annotation, methodology, and troubleshooting. Here is our original project plan. We designed this project to have data inputs, pictured as green orthogons, to feed camera and humidity data to the microprocessor. After running the visual data through an implementation of yellow 4 tiny, the resulting probability, if above the threshold, would trigger an alarm. If not, the humidity data would be assessed and trigger a simple warning if enabled and loop back to repeat the process. When classifying the images for the convolutional neural network, or CNN for short, we chose to minimize the number of classifications to three things: fire, smoke, and no fire. The reason for this was to include fire-like adversarial images as no-fire classifications to delineate fire from other sources that typically could be classified as potential fire sources. We also included smoke as an indicative classifier to reinforce the fire confidence. Here you can see examples of the annotation of the adversarial images to better train the CNN. Due to hue and prominence and saturation, a primarily red room and extreme contrast lighting sources were needed, such as those pictured. In total, we annotated 565 images, with about 60% of those being fire images and the rest being non-fire. To better understand our results, we looked at the confusion matrix and accuracy of the model. Unfortunately, due to the need of using a faster, more lightweight CNN for evaluating the camera input, the overall average precision of the trained CNN we choose to use was only 86%. This rating was too low for real-world applications, where a 1 in a million false positive rate is expected for utilization. You'll need to improve upon this rate in future iterations. Jarek will explain the deployment next.
Hello, I'm Jarek, and my work on this project was focused on the training and deployment of the neural network. We had tried different levels of training as our dataset grew larger. From the chart that you see here, this is a model that was run for a total of 10,000 iterations compared to the recommended 6,000 iterations per 3 classes. As Chris mentioned, we decided to use a model run for less iterations and with a lower resultant precision from training. The problem with running with more iterations causes a higher chance of false positives due to overtraining the most represented class in the image dataset. I was able to train locally on my machine, taking about 2 hours per model. This short video demonstrates the model detecting a fire from the lighter when run from my desktop and webcam. Despite using the tiny model, the Raspberry Pi is not capable in processing it. To work around this, the model is converted and optimized to Tencent's NCNN framework. This framework is designed for use in processing performance found in mobile phones. The code that you see on the slides are derived from the official NCNN repository examples. It is in C++ from an existing project by Q Engineering in the Netherlands. net.h is a header called from the NCNN library, and a few OpenCV libraries are added for handling inputs. The modifications I made here are in the class names we will be detecting with this model. As Chris mentioned, were fire, smoke, and no fire. The next functions declared, which are not pictured, are the object detection and labeled box drawing functions. Here in the main function, the trained model that was converted from YOLO to NCNN format is loaded. Originally, this program was set to ask for an input JPEG file, but I modified it so that it will continuously capture frames from the default camera index until the user hits Q from the camera window to exit the program. This video is a demonstration of that code in runtime. The camera is a standard Raspberry cam that can take images up to 1080p, but when run as a video in this resolution, the frames are processed much slower and the camera signal becomes garbled and discolored into a bluish color space that does not detect fires. On the other hand, lowering the resolution causes decreased detection and accuracy, so running at 720p was the only passable option for detection. You can see from the video that a fire, represented by a null class, only appears for a couple of frames for the whole video. As mentioned, the camera is mounted on a servo, which Noah will now go over.
Hi, it's Noah again. I'm going to talk about the part that I focused on, which was the servo and the camera mount. The wiring of the servo consists of a signal wire going to pin 11, which is the GPIO pin necessary to send a PWM signal to the servo. Then we have our ground going to pin 6, and our 5 volt to pin 4. We went with the continuous rotation servo, as the regular micro servo would not be sufficient. We took the FOV of the Raspberry Pi cam, which is approximately 62 degrees, to determine that it is necessary to have 6 different positions of the camera to cover a full 360 degrees. As shown in the diagram in the bottom right corner, we have 6 different camera stop positions, 60 degrees apart. As I started researching the programming of the servo, I realized that it did not have a potentiometer, which is a key component to allow the servo to recognize its position. I had to work around this by changing the duty cycle and using a protractor to get approximate angles within 2 to 3 degrees of the exact. Here's a short demo of how the servo works. In this video, we are making a full counterclockwise rotation and then a clockwise rotation, each stopping in 6 different positions. This video is also sped up. Let's briefly go over the important parts of the code. I set my pin 11 as my output pin and gave it a 50 Hz signal, which is the input frequency the servo requires. Then I started my first while loop for the first counterclockwise rotation for 6 stop positions, and another while loop at 6 stop positions in the clockwise direction. Here's a quick demonstration of the camera view while the servo is running for the first set of rotations. This video is at 2 times speed, or So I will now go over the wireless sensor network.
Hello, my name is Saul and I primarily work on the wireless sensor network. So a general overview of the system will consist of a central node where all other sensor nodes will transmit to. As you can see, once the data has been gathered by the moisture sensor, it then proceeds to transmit the data to the central node. The central node will then display the reading to the LCD screen and will check if it is above a certain threshold, in this case 20%. If it falls below this threshold, then it will trigger the alarm but can be silenced using a button. In total, we use 7 components to construct this system, 5 for the central node and 4 for the sensor node. The central node was constructed from the Arduino microcontroller, transceiver, LCD screen, buzzer, and button. Moreover, the sensor unit was constructed from similar components such as the Arduino microcontroller and transceiver, but also included a battery and a moisture sensor. The total cost for the central node and one sensor node came to about a total of $100. The central node's main features are the following. The central module can be powered by any plug-in outlet in your home in conjunction with a 5-volt AC adapter and a USB to mini B port. As previously mentioned, it displays moisture levels from surrounding nodes, and below a set threshold level triggers an alarm. In addition, a button to silence the alarm. As you can see on the right-hand side, you have a front-facing view of the central module and it displaying a soil moisture reading. Here is the overall schematic for the central node and how all the different modules were connected. An important connection to mention would be the inter-integrated I2C pins highlighted in red. This form of communication protocol enables us to use the LCD with significantly less GPIO pins than a traditional LCD would have. The sensor node's main features is that it is able to transmit up to 135 meters long. This was done in a residential setting, so the range could be higher in an open setting where there are no obstructions such as other houses. As previously mentioned, it transmits every 6 hours and can run up to 11 days. The battery can then be recharged using a micro USB cable. As depicted in the image, you can see the aerial view of what 135 meter looks like, particularly from the Walter Stern Library from the CSUB campus. Here is the overall schematic of how the pins were connected to the Arduino microcontroller. An important connection here to mention would be the pins D11 and D12, which are the assigned SPI pins on the microcontroller. SPI stands for Serial Peripheral Interface. It is the de facto synchronous communication bus standard. It boasts both simple implementation and high-speed data transfer capability. Here we are using it to transmit data to the transceiver so it can be transmitted to the central node. The antenna was constructed using a strand of solid core wire. For the antenna to be functional, we created what is referred to as a quarter whip antenna. To determine the length of the antenna, calculations needed to be made. The length of the wire is equal to 1/4 of the wavelength. Therefore, if we look at the equation for wavelength, we can calculate it using the speed of light, which is 3 times 10 to the 8th meters per second, and the frequency being used for the transmission, which is 433 megahertz. Evaluating this gives us a result of 17.3 centimeters. To the right, you can see the antenna soldered to the transceiver breakout board. So for our system, one library used was Radiohead, which was created by Mike McCauley. As you can see, it provides a lot of functionality for setting up the transceiver and implementing it to your will. The second library we used was Liquid Crystal I2C, which was obtained through John Rickman but listed 10 other contributors on GitHub. This library needed to be used due to the LCD screen using I2C serial communication protocol that is very similar to the Arduino Liquid Crystal built-in library.
One aspect that really needed to be addressed with transmitting and receiving was converting the moisture sensor reading from the sensor into a format that would be transmitted successfully. Using this library, transmission occurs in packetized bits. Therefore, we need to break the sensor reading value into a single character bits, which could then be transmitted and received correctly. Now the demo. Before we play the video, I would like to provide some context on what you will be seeing. So the total distance between where the central unit and the node is about 15 meters or so. Here in the video, I will be taking and transmitting the moisture level every 3 seconds. But as mentioned before, the final product will be taking moisture levels every 6 hours. The threshold value will be set at 20% in accordance with the final product's threshold value. Starting the video, you will see the sensor embedded in very dry soil. Therefore, the alarm will sound off. I will then proceed to continuously add water to increase soil moisture levels. I will also be continuously pushing the button to turn off the alarm after each reading until it exceeds the threshold value for the alarm. So as you can see in the video, the central unit will be booting up beginning now. And since it's below the threshold value, the alarm is going off. And you can see me in the background going out to pour more water. So now it's still at 20%. So it's still equal to the threshold level, still making the alarm sound off. Now above the threshold level, the alarm has been disabled. Chris will now address the timeline of the project.
Hey, Chris here. This is the original timeline for our project. We did complete all but one task on the timeline. However, the duration of each task varied from our original expectations. We did not account for several setbacks, including several instances of hardware failure and a delay in funding. As a result, to meet timeline milestones, we were forced to compromise on software and hardware used due to resource availability and timing. Examples include using YOLO instead of our own CNN, images without IR spectrum for training, and foregoing the development of an external chassis for the camera. The challenges we experienced for this project, um, many of them could be tied to COVID restrictions. Until the entire group was vaccinated, we were unable to meet. Due to the ambitious nature of this project, the scale and shortfalls of the project were not fully accounted for in the initial project description. We had several pieces of hardware that were faulty or not up to specification, which added lead time, or not having the appropriate part due to funds. Another difficulty faced was limitations of the Raspberry Pi. Running programs simultaneously on the Raspberry Pi also affected the consistency of the servo rotation, as well as the speed of the object detection program. Project learnings and plans. The project was very educational when coming to terms with expectations and collaborations in a virtual setting. Microsoft Teams made it possible to work remotely for the full course of the project. Teams is incredibly flexible for collaboration, combining file sharing, chat client, and task/deadline setting. For future iterations, we plan to add an IR sensor and use a camera with a normal recording space and a focusable lens due to the incidental bleed caused by IR radiation. We'll also be adding additional annotated images to the training library for further reinforce the CNN accuracy. and using a 360-degree servo with feedback to accurately determine camera position for recording, and add a second servo to allow y-axis rotation. Additionally, we will implement a specialized CNN and move from Raspberry Pi OS to an onboard implementation to improve performance.
To wrap everything up, it is possible to have an implementation in the initially proposed scheme. The processing speed can be improved with the use of a different single board computer with an onboard GPU or a neural processor stick added onto the Raspberry Pi. As Chris mentioned, we need to refine the neural network for the object detection to be passable as a safety tool and for the purpose originally intended. Lastly, consolidating the code and integrating the wireless sensor network will be necessary to utilize each component to raise the same alarm and make this project more complete. Overall, it was an enriching experience attempting to provide a solution to a complex problem. We thank you for your time listening to our presentation.